Ladies and gentlemen, I would like to present Eurocode concrete design with Singaporean annex. Now, something happened. Okay. In this presentation, we will introduce our speakers shortly. Then we will see Eurocode hierarchy. We will introduce Eurocode 2 with Singapore National Annex. Then I will show you a couple of examples of Eurocode design of cross-sections, beams and details, and I will make also some comparison with British standard. Then we will concentrate on Singapore nationally determined parameters, and we will tell you something more about our company activities in Singapore, and then we will finish with questions and answers. Speaker's profile. My name is Jaroslav Navratil. I got the master degree in '86, last century, then PhD. But what is more important is that I lectured more than 25 years at Brno University of Technology. That's why I became, I would say, quite experienced in concrete, pre-stress concrete structure analysis. And last 12 years, since the beginning of pre-code of Eurocode, I was lecturing the Eurocode. I'm chartered engineer and forensic expert in civil engineering. I wrote more than 100 research papers and textbook on pre-stressed concrete structures. Eurocode StatiCa became master in 2011. He also studied Singapore Management University, working 2 years in corporate banking and 3 years for IDEA, our company. Now Eurocode hierarchy. You might know that Eurocode is split into several codes. Eurocode EN 1990 is the code dealing with safety and durability concept. You get the information of how to combine the combination of loads and what is the reliability and so on. Eurocode 1991 is about loads. It has several parts. Different part for snow load, different part for wind load, for moving loads, etc. Then we have a group of structural design codes. 92 is for Eurocode 2, which is concrete. 93 is steel. Then composite, steel, concrete, timber, and masonry. Then we have 2 codes for geotechnics and seismicity. We will be focusing on Eurocode 2 in this presentation, and especially Eurocode 2.1.1, which is Eurocode for general rules and rules for buildings. We have implemented also EN 1992.2 in our software for concrete bridges. And there are also other parts as you see on the screen. Building and Construction Standards Committee of Singapore approved Singapore National Annex in 2008 year, and since April 2013 Eurocode became an official regulatory standard. Of course, we implemented this Singapore National Annex into our software, and you can see the differences between standard Eurocode. You will see the differences in today's presentation. This is the way which we implement national annexes. As you see, we have these annexes, and it is possible to be edited in code and calculation settings. Each provision of the code can have a special Singaporean parameter which can be changed or which can be reverted back to standard if necessary. Now I will show you a short presentation or short example of the design of reinforced T-section. I will start the program, IDEA Concrete, and I will create new project. You can set the national annex here. You can select the type of section, and after you do it, the window is opened in which one section is defined. You can see you can edit this sectional name, and you can select the cross section. The cross section can be predefined or general one. I will select predefined section now. You can edit these geometrical properties, and then you get reinforced cross section shape. After you select the reinforcement, we have predefined templates for reinforcement. So number of upper bars will be like this. Number of lower bars 3, diameter 16, and stirrups diameter 10 millimeters, this stirrup distance 20 centimeters, and we can say OK, and we have defined the reinforcement. Then we can set again the exposure classes for our cross section, and we can input internal forces. In this case, it is a standalone program for cross section, so we have to define, for example, shear force 90 kilonewtons, torsion 20, moment 145, my, mz would be 20, let's say, and here I would have 120 and 100 for characteristic and quasi-permanent combination. You can see that there are two tips. What the combination is like. It is a serviceability limit state combination, and the first one is ultimate limit state. For concrete cross sections or concrete structures, reinforced concrete non-pre-stressed, there are two significant combinations for serviceability limit state and one for ultimate limit state according to Eurocode. Once I defined it, I could also use, for example, the import from other our programs from Beam or Frame, or I can copy this table from Excel program. I can calculate by this using this calculator the section. It is already calculated, and in info window you can see the results. You can see what type of check is satisfactory and what is not satisfactory. You can go to checks. You can see the list of checks which we have. In settings, you can say, for example, that you also want to have stiffness or a response, and in spite of the fact I see that there are some checks which failed, I will show this response first. This is a stress-strain response of the cross-section which we are going to design. You see this is a strain distribution, and here is stress distribution. You can see probably the parabola here in concrete in compression. You can see neutral axis. Here these crosses are the positions of resultant forces. This is the most tangent reinforced bar, and this is the most compression pressured concrete fiber. You can switch also to 3D or 3D forces, where the resultants are, or the diagram, and to observe which fiber is loaded in which way. You see here in this point 1, we are on this position of the diagram. For example, in steel, we are on plastic branch. In this steel, it is slightly smaller, and here, for example, we have even less stress. So that was a short introduction, and we now see that there is crack width which failed. Crack width, you see the distribution. You can see short term and long-term distribution, and you can read that your crack width is 0.356 millimeters. Limit value is 0.3, which is 118%. You can identify that it is for short-term effects. Here you can read intermediate results. If you want to check the program, it is a clear open box which you can always check. So intermediate results and possible nonconformities and explanations. So we see that definitely this crack width needs more reinforcement. Let's go back to reinforcement. We select this layer of the reinforcement, and I will input 4 bars instead of 3. As this reinforcement gauge was used using these templates, the program knows that it is in one layer, and the program knows that there are some detailing rules. So if we enter 4, the program identified that 4 cannot be placed in one layer, and automatically offers 2 layers with symmetrical reinforcement of 5 bars, which you always can select and explode, which is here, explode layer, and delete one of them or make it in the other way. Once we changed it, we can calculate current, and you see immediately that crack width is already satisfactory. The only which is not satisfactory is interaction. This is a feature which we are proud of, and it is possible only because we use Eurocode, because of the theory accepted in Eurocode. And before we go to interaction, I will show response again. Now we see a little bit different response. You can remember, for example, this strain or this stress. And now if you go to interaction, you see that it is bigger. So we apply the tensile force caused by shear and torsion to the reinforcement which is in the cross-section, and we see that the response is different. But what we see here, the check which failed is the check of the combination of shear force and torsion, and the program tells you that this 250% is equation 6.31. If I switch to Eurocode and I say that I want to see the equation 6.31, then you see that it is really the interaction formula for shear and torsion, and the program even tells you these are intermediate results, and program tells you shear check is not satisfactory due to insufficient strength of shear reinforcement loaded by combination of shear and torsion according to clauses 6.2.3 and 6.3.2. So you immediately know that you have to change the reinforcement. Before I do it, I go back to response, and you can record again, for example, this stress. It is almost 11 megapascals, and here we have 314. If I go to reinforcement and I increase the diameter of a stirrup from 10 to 12 millimeters, now in fact I changed the lever arm by 1 millimeter, because it is 1 millimeter below and 1 above, so the lever arm changed 1 millimeter only. It is satisfactory already. If I go to response, I see that I have here 1 megapascal more. So the program is able to recognize also such small change like 1 millimeter change of position of the reinforcement, and it will tell you what is the difference or how it is checked. So this was a short presentation of IDEA Concrete. I hope I showed you that it is effective and easy to use. If I was not talking about, we could have the results in 10 seconds. But at the same time, it is comprehensive, and it will lead you in a way so that you can be oriented in Eurocode. So it is Eurocode supported. And as we use latest technology, it is also a high-tech solution. And now I will present some features of the analysis based on Eurocode. What is in Eurocode here in chapter 6.1. I will show. There are basic assumptions of how to analyze the members loaded in the combination of normal force and flexure. You can see the assumptions directly on the screen when you use our program. You see this parabola, plastic branch, here in fact bilinear diagram of non-pre-stressed steel, neutral axis. So your program will immediately tell you what are the assumptions of the solution. And as you see, there is no stress block factor simplification, nothing like that. The analysis is really comprehensive. For pre-stressed cross sections, we have even a more sophisticated solution. Here in last assumption, it is said that you have to use initial strain in pre-stressing tendons. So what we do is that we really apply initial stresses as a result of the action of dead loads and creep and shrinkage, and we add the effects of variable loads, and we calculate the total effects here on the right hand side. In each fiber of concrete and in each bar and pre-stressing strand, we respect the position on stress-strain relationship. So there is no simplification in the solution, and we comply these Eurocode assumptions fully. About the truss model, shear design, this is a little bit new compared to other codes or old codes. We use, or Eurocode uses truss model for shear design. You can see here the picture from my book, which is the element loaded in pure shear, as you can see. And we see that there are 4 unknowns. Of course, the stress or force in the stirrups, the compression in the strut, concrete strut, this angle of the concrete strut, but also the increment of normal force in the longitudinal reinforcement. And this is something which we use later for the combination, for the analysis of interaction of all forces. I'm not going to the formulas because of limited time which we have now. Torsional resistance according to Eurocode is calculated using equivalent thin-walled section. So it is based in fact on a kind of application of Brett's formula, and the program which I showed you identifies this equivalent thin-walled section automatically. And as we all know, torsion also results in a longitudinal force, in longitudinal reinforcement, which we use again for this interaction of internal forces. Here we have only the interaction of shear force and bending moment. But I believe that this interaction was not possible in our old codes before Eurocode came. You can see that this is the increment of the force in longitudinal reinforcement caused by shear, which I have explained. And here, as everybody knows, there is an increment of forces in longitudinal reinforcement in bottom and top bars caused by the bending moment. If we add them, we get the final results, final force, and we check the force. This can be drawn in an interaction diagram between moment and shear force, which was not possible before. This is, of course, picture from Excel. It is not made by our program, because what we do is, in fact, it is interaction of all these components, as I show on the top. All components of internal forces are checked, so we would have to draw a picture in 6 dimensions, which we really do not know how to make it. Now is this the explanation of the way how we do the interaction, how we respect interaction. Here on the left hand side you have the bending moment response only, caused by the bending moment. You see the force, the stresses and strains in the reinforcement, and we calculate the strain caused by shear and also torsion, and we add these strains into the bars which are enclosed by the stirrups, which are effective to resist the torsion and shear. And then we get different, of course, different strain and different stresses, and these are checked. Because I have limited time here, I wanted to only to display all the serviceability limit states checks which we do with reference to the provisions of Eurocode. Maybe I could mention this status cracked and uncracked cross-section, which is required by Eurocode, which makes also this stress limitation. We can call it also allowable stresses or permissible stresses, as we know from other codes, which makes this analysis quite complicated, because it is in fact non-linear. Also other checks are done in the program, including crack width and so-called decompression, which is again a little bit confusion with the method of decompression stress and decompression force. There's nothing common. This is only the condition of compression reserve, which is required in the case of certain exposure classes. I will show later. Of course, deflection control. Now I will show you briefly the analysis of a reinforced beam, and I would like to use our cloud system. Now I am in the browser on internet. In fact, I do not need our program downloaded and installed in my computer. I do not need the license. I use it only as a service. As this is not a topic of the meeting, I will not be explaining the system. I will immediately go to calculation, and I will sign in via my Google account. And now I am already in the system. I see that I have 36 credits only, and I can analyze the beam. And this is the beam which I want to analyze. Now the program is running somewhere on the computer farm in Ireland, and I'm located, of course, in Central Europe. I use my browser as I would read the newspapers, and on the background, finite element analysis and design of members and sections is performed. I start new beam. I use concrete beam, single span. Sorry, I will use continuous beam. The spans 6 and 8 meters. I will use the cross-section T section. From this we can use also advanced, also this one. I will use T section, which will be 600 millimeters deep, 1000 millimeters wide. The web would be 350, and the slab was 180, I suppose. This is a real example, concrete 3037, real example of the beam in the design of one wine cellar, which is in South Moravia in our country. Permanent load in that case was minus 20 and variable load minus 5. I want the program generates the critical load patterns with zero load on unloaded spans. Now I finish and my beam is generated using that wizard. I can see all these permanent load factors defined in Eurocode EN 1990 and also variable load factors which I can change. We use the default which is quite common in overground structures, but if you see the tables in EN 1990 you can adapt it. Of course we can change the settings here. We can check the cross sections, possibly change the cross section. We can edit the material, see what are the properties of materials. We can check the members, add the member or delete one. We can define even the haunches, but here in this example it was not the case. We can see the load cases defined by the program. Here, for example, we have these spans for critical positions of the load. Here is the total load, and here are the factors applied on each load case. Of course, we can define exclusive or standard load case, and the program will find automatically the critical load patterns according to Eurocode EN 1990 using these coefficients from 1991. I can define point forces, which I do because it was the task in this example. So my force will be minus 30 and it will be in member 1 in position 3 meters. You can see now for live load or variable load, as they say now in Eurocode, we can define minus 20 force in 3 meters, and this I have to input it also for this load case. When the first span is loaded, then I define the same load in 3 meters. So now I have defined this, and I can see also other possibilities of input of point moments, uniform loads, line loads, settlements, and I can see the combinations. Now selected combination is with these factors, but the factors according to code, as you can see here, it will be evaluated according to code. You can also see the possibility of envelope and linear combination. So these real factors according to Eurocode will be generated automatically. Now I calculate the structure again, and I see the reactions caused by ultimate limit state combinations or deformations. See that there is an envelope of deformations and internal forces. Again, envelope of internal forces. If I am happy with the results, I see that there is this peak caused by, I can use even this load cases, for example this one. You see there is a peak caused by this point load. I can go to concrete design and I see that I predefined all the checks which I need to check. I predefined this exposure classes. Usually in the beams inside of the building we have carbonation only XC1 and no risk of chlorides. We can adapt also other data. We can define the reinforcement. Now the program tells you that we start to enter paid part of IDEA StatiCa website. Until now we performed all the calculations for free, and we see the cross sections which program offers and the zones of reinforcement which program offers. Here we have also the bending moments which are calculated, and we see that as this span is shorter, then the bending moment is significantly smaller. It is approximately the same as here in the right hand side, this zone AA. So probably we can select this BB zone and we can delete it. Now we have the same zone AA as here, which will resist the same, approximately the same moments. Program identified approximately the positions of the inflection points, but as it was non-symmetrical, we can or we should adapt here this zone to 1.8 meters to get really the change of the reinforcement in inflection points in the point where the bending moment is 0 or approximately 0. Okay, we defined these zones, and we can now define the reinforcement. As you see, we have several possibilities, several templates for the reinforcement, and we can say, for example, in zone AA, my upper reinforcement will be 4 bars because of the stirrups, but 10 millimeters is enough. The number of lower bars will be higher for diameter 16, no side bars, no edge bar, and the stirrup diameter 10, 20 centimeters distance. Program tells you the list of reinforcement, and now we see if I select the line, the reinforcement is drawn here and also here. If I select CC zone, I again edit it, and I say I want to have different reinforcement. Of course, there is negative moment, so I will have 10 bars, diameter 16, but the moment is really big. That's why I need also compression reinforcement, 3 bars, diameter 16, and I will need 1 bar on both ends, diameter 10. And my stirrups, of course I tested it, was not enough for at the distance of 20 centimeters, so I will design stirrups of diameter 10 at a distance of 12.5 centimeters. I hope I defined all correctly, and I can say this is my reinforcement I see now. And BB, this would be exactly the same. The reinforcement will be different. Upper bars will be diameter 10, lower bars will be 5 bars, diameter 16, and we need here also edge bar. I wanted to save time, that's why I tuned the reinforcement before. I can see the settings for deflection, and I go to results. Now the program calculates all the types of the checks in the sections along the length of the beam in all zones. It is calculated in on my computer. It is on the internet, as I told you, in this farm. And now we have the checks. It is satisfactory. You can check not only the overall check, which is 100%, but also capacity. Now you see there is a difference above the support, shear, interaction, stress limitation, and crack width, and also the detailing. Of course, you have a summary, you have a bill of material, because it tells you that, for example, there is 11,445 kilograms of concrete, also reinforcement, and all other reinforcement per cubic meter, and all other parameters. Here the pictures of the reinforcement in the zones. You can see the detailed description of the checks in each zone, and you can see also the deflection check, which is here, which I can show here. Now we see the deflection. We can select these different combinations characteristic combinations or serviceability limit state combinations. So this looks, this is the biggest one. We can check linear. See, there is another. Linear is very small, immediate deflection and long-term deflection, and limit. If we want to study it, you can see also stiffnesses, immediate, long-term, and total. So this is the stiffness. As I told you, it was non-linear calculation along the length of the beam. We adapted the stiffness. We can, of course, generate the report and so on. I think I will close this without saving. No. And I go back. I go back to my presentation. What I expected that you would be interested in the comparison of Eurocode and British standard. That's why I made an example which I took from the book of Kong and Evans, Reinforced and Pre-Stressed Concrete, 3rd edition. There was an example, simple one. You see the cross-section, and I calculated the deflection of the beam in our program. Here you see the distribution of flexural stiffnesses along the length of the beam, and here you can see the total deflection or comparison of total deflection. In the second column you see the results of Evans, Kong and Evans. I have to say that they used concrete C40, which is cube strength, as you definitely know. That's why I expected that cube strength 37, according to Eurocode, would be appropriate. But then I realized that a modulus of elasticity, which was used by Kong and Evans, was 28 gigapascals. But, and it was, according to code I calculated it yesterday, it was slightly more, but they used 28 exactly. According to Eurocode, you can find in the table that it is significantly higher, higher modulus of elasticity, which is already one comparison. The moduli of elasticity defined in Eurocode are quite higher than based on British standard. This I do not consider as a positive feature, and I would like to warn you, because in case that the producer of concrete really wants to make a nice compressive strength, then they use admixtures which will make the modulus of elasticity lower. So I would say this is not very realistic value. You also see the difference in the calculated deflections. It was 17.9 according to Kong and 16.1 according to Eurocode. When I tried to select, I would say, lower grade of concrete, so that my modulus of elasticity would be closer to the one which was used by Kong, I got the deflection 16.4. First reason was that still the modulus of elasticity is a little bit higher, but what more, Kong and Evans did not take the tensile strength of concrete into account, which is significant. The section was fully cracked. There was no tension stiffening. In fact, I know from the past that British standard simplifies the tension stiffening effect. I would say it is a little bit illogical that without any regard to the real stress-strain state, the British standard asks for, in case of short-term effects, that we put 1 megapascal in tension in the concrete, and for long-term effects 0.55 megapascals. Contrary to this, Eurocode uses, I would say, more sophisticated approach for tension stiffening effect. You see this state 2 is the response of bare bar, and the shaded area is, or gray area is the effect of tension stiffening, which means that the deflections calculated according to Eurocode will be lower, smaller than the deflections calculated by British standard. And I would also say more realistic. Another difference is the Strut and tie model. Eurocode tells you this is 651 provision. They say in that discontinuity areas you should use Strut and tie models to verify these details. This is just illustratory picture from Eurocode, and this is one of our applications for details. This is a bracket or corbel if you want, and I want to show you this briefly again in our cloud system. So now you see I have bracket. I can start bracket. same principle. I'm again on internet. I start new calculation. I will not be going through all this to save some time. So you see that I can define the materials, concrete and steel. I can define the geometry. All these parameters of the bracket and column, bearing area and everything can be defined here. I can define the reinforcement. For example, these are primary space looped bars, but I can also use this one as a primary reinforcement, looped bars, or I can use framing bars. I can use vertical stirrups and horizontal stirrups. We can see this axonometric view or standard view with dimension lines and concrete cover, and all these is possible. Then I go to load items and I defined only one. This is a not load case, this is a result of combination of loads. And if I have all done, I go to checks. Again, the program tells you that you go to paid part of the portal, and you see that there are all checks. Of course, we check all these checks. I will show you these members. This is a real Strut and tie model. I will remove the reinforcement so that it is more clear. We see the strut, which is in red color, the nodal zones, and the tie. We check all the members of the Strut and tie model, which you see here. A strand of strut, tie, nodal zone, detailing, vertical stirrups, horizontal stirrup, anchorage length, mandrel diameter, all these checks are done. All are satisfactory here. Here you have more detail output. And you can also see the forces, as I showed you, which you can check and you can define. You see there is also a horizontal one, so it is a little bit inclined. And here is the reinforcement, which should be safe to carry this. And we can also generate the report. I will again close this file, not save, and this one I close. So this was last presentation of our cloud portal, and now I will just demonstrate the example of a pre-stressed continuous beam, which I will not input because of the time, but here I generated in the same way as I showed in the cloud. I generated 3-span continuous beam, which in fact is a part of the shopping mall in the town of Ostrava in North Moravia. And what I did was that I pre-stressed it. Now I start the module for IDEA pre-stressing, and I pre-stressed it. Those are a kind of construction stages, design members and tendons. I can make this scale more appropriate so that we have now scaled scaled the picture in XZ plane. You see the tendons. You can edit the tendons, change the geometry XZ. XY is here. You can see the force design, so equivalent loads. If I switch off this XZ load balancing, you can use for the design of pre-stressing, losses of pre-stressing, then member results. Here we have the effects of pre-stressing, which we can use also. We can show primary and secondary effects. We can show all ultimate limit states. Now we see the envelope, and we can go to design member check and define several positions for check and run detailed calculations. I'm not showing everything, not about this info window now. The same program as you see in the first presentation of pre-stressed beam. You see here we have 3 sections which are with tendons. Here is the tendon, and I can select other one which is above the support, for example. This one is above the support, and I can it is already reinforced, and I can go to checks, for example, to response, and I see the response of it is calculated. This extreme is already calculated. The other extremes, because it was generated and plenty of extremes was calculating. Here is the progress bar. So after all of them are calculated, we see the picture of the response of this pre-stressed section, and everything which I showed before is possible. Just the last comment. Those are, as I show it now, oh, it's more. Those are the extremes calculated in 14 days when it was pre-stressed, and in 100 years when it was when is the end of the service life. Now I go back, I exit this pre-stressing, and I see it back in the beam program. Let's go back to the presentation. I didn't mention in live presentation, but you might have seen the tendon spacers. Of course, this is a practical program. We calculate the positions of the tendon, or better said, for a predefined depth of the spacers. As you see, 200, 500, 800, and 1200 millimeters. The program will calculate the X distance from the end of the beam in which you should position this spacer, and of course you can export it to the XF. Now we go to another example of Eurocode design, which is pre-stressed concrete section, and I would like to open, I will close this, and I will open the example which I have prepared before, and in fact I defined, you can see it in info window. This is the same which I showed you in first presentation. This is, I can show here, the bridge pier, which was about 15 meters tall, general cross section with the reinforcement along the edges of the pier. Here we have shell slab element in one point of the shell, which can be loaded by 8 components of internal forces, and you can check it in this point. And the last one is the pre-stressed one, which I wanted to show. I defined only two extremes in 7 days and 50 years. Here you have the reinforcement of this, and we can see, for example, just to show the response, and I can use these dimension lines And this is the response in 7 days. You see the distribution of stresses, and here this is the response in 50 days. You see that due to the losses, long-term losses, we have smaller compression and even tension in this edge of the cross-section. So this was, I will be showing this example later, so I will switch into the presentation, and now I will focus on Singapore nationally determined parameters. I selected only some of them. First of them is this alpha CC coefficient. You see that it is used to calculate the design strength of concrete for long-term loads. So standard value is 1.0, but Singaporean value is 0.85, which means that in case that you have significant portion of long-term loads, your design would be safer. Here we have another parameters nationally defined in Singapore, R sub and R inf, which are the coefficients or factors used to multiply or to increase or decrease the pre-stressing force. You can see that standard value for post-tangent concrete is 1.1 and 0.9. Singaporean values are 1.0. In this case, I would say it is very reasonable, and I congratulate the committee to this decision. Our committee in Czech Republic did not do it, and I think it's a little bit impractical, I would say, to design the structure for the scatter of 20% of pre-stressing force. It really makes the problem, and if you measure the level of pre-stressing force in the pre-stressing tendons, and you do it and you record it during pre-stressing, then I think it is not necessary. I will show in this example presentation, here we have defined, you will see the project data, and we have defined Singaporean annex. Okay, we have Singaporean annex here, and you saw that the cross-section is satisfactory. You have Nike here and 2 Nikes here, so it is satisfactory. All this is okay. And if we switch into a standard Eurocode, it must be recalculated. So I can recalculate all. This is already done. This is there is hundreds of reinforcement bars, so it takes a little bit longer. Now it is finished, and now pre-stressing, and you see there is this extreme is not satisfactory. We see that stress limitation is 4% more. We go to stress limitation. We see the response, and the program tells you the provision 6.23 for quasi-permanent combination subpremum of pre-stressing reinforcement, concrete fiber number 6. We can switch on concrete fibers. Bars numbers, concrete here outside. So we see this is this one. It is even marked by the red label. It's not okay. It tells you why. There is a 14.63 megapascals, and it should be 14. So simply by changing these settings for national annex, we see that it is not satisfactory. Now we go further. Another difference is the coefficient taking account of state of the stress in compression hold in shear analysis. This is again a picture from our program. You see these national parameters defined in the settings, and we see that there is difference also in the maximum reinforcement ratio for shear reinforcement. I will demonstrate it now. So now we have defined standard Eurocode. We can, in fact, we can switch it into Singaporean, and it's calculated now. We go back to the shape. You see everything is satisfactory. Here you see it is 100%, but this is detailing only, so the rest is okay. We go to shape, and first what I need to do is that I change it here, the web thickness 220 millimeters instead of 260, so my web is thinner now. And I also want to change this distance of stirrups, because there is a significant force. It was 130 millimeters, and now I say 125. Now I go to response, and I see that my detailing is not okay according to Singaporean annex. I go to detailing, and program tells me that it is 28% more, and it is here maximum reinforcement ratio for shear reinforcement according to 6233. Okay. Now we go back to standard Eurocode. Okay, and we see what is the result. The detailing is okay. It's no problem with this maximum reinforcement ratio, but stress limitation is not okay, and that's what I explained before. It is the result of the coefficient R sub and R inf in the pre-stressing force. So we see that there are quite significant differences. Another difference is in crack width. You see that here, this is a standard table in Singaporean National Annex. Here is the table from our program, from standard Eurocode, and from our program for Singaporean Annex. You see that there is a different crack width. Probably you have the sea very close to, so probably the crack width 0.4 would be too big. So I just wanted to show that there is a difference. I will not be demonstrating. By the way, here we have a decompression condition, which is also in Singapore, and here, which I mentioned as the condition for compression reserve. One of the last slides here is the summary of competitive advantages. I hope I convinced you that we have a proper implementation of Eurocode. We always want to have up-to-date version. We have real practical experience. We are a company which sells Eurocode design in 10 European countries. We are the country in which Eurocode is valid more than 2 years, and in which already pre-codes were taught and lectured at the university. So it could be expected that our I would say implementation of Eurocode would be a little bit better than from other countries in which the Eurocode is not native. We have Singaporean annex, and after Singapore agrees and approves the annex for steel structures, we will of course implement it. As you might have noticed, we have educative and supportive software. We also have a kind, or our way of BIM, because which I didn't show, maybe I will show it later. It is linked to various 3D packages. You saw that it was checking software. You can analyze any shape, any reinforcement which you define, and you can get detailed analysis. modern user environment is a result of the fact that the program is quite new. Our company is only 4 years old. So we started from scratch and used modern technology. And I also demonstrated our cloud.
So as Jari said, basically develop designing tools, focus designing tools to help engineers to cope with concrete, steel and pre-stressing tasks. We do it both offline as a standalone license, you know, and in cloud version as well, which is only using a web browser. And we also link all our programs to software solutions on the market. Our drive is to make every new construction safer and cheaper. Those are important facts because everybody wants building not to go down, but the issue is growing to be to make it effective. Okay, Jari, can you give me the next slide, please? Just a quick info about where do we come from. We are a Czech-based company. We have an office in Singapore, and we came here as a part of the intergovernmental program between Singapore and Czech Republic, which offers innovative companies to come to Singapore, spend half a year there, and start their operations. We had various seminars on Eurocodes here. You can find more information about them at our website. We also started cooperating with universities, planning to do joint development projects. We have our first customers in Singapore, and we our software is recognized by Building Construction Authority. They have the licenses, tested it, checked it. Now it's place for Q&A. Basically anything you are interested in discussing more about Eurocodes, you can type in the questions into the chat menu on the right.
Then I would like to thank you for your attention, and as the last pictures I prepared the special example of the analysis of cross-section in the shape of the head of Singaporean Merlion, as you can see here. So this is a cross-section which was deep 2 meters and wide 1.6 meters. I defined some non-pre-stressed reinforcement around it. I defined also 3 pre-stressing tendons, strong one. And this is a distribution of strains and distribution of stresses. You see that there is again parabola with plastic behavior of most compressed fiber, and this bilinear distribution of the stresses in the reinforcement. Here you have again this position of the stress on stress-strain relationship. Here you have a 3D view of this cross-section, and last picture is the position of resultant forces. Once again, I would like to thank you for your attention, and if there are no questions, then I would finish the meeting now.